So we saw this pattern at the end of the last video. If you want to generate a polynomial approximation of a function, and the function you're trying to approximate isn't somehow related to 1 over 1 minus x, so that you can just transform a geometric series, you're going to use the derivatives, as many derivatives as you can compute, to build that polynomial term by term. And this pattern that we have here, f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial, and then 3 factorial, and then 4 factorial, all the way up until an infinite number of terms. That's the way to generate a Taylor polynomial or a Maclaurin polynomial. Remember, if we're going to center our series at around x equals 0, you can call it Maclaurin. They're all Taylor polynomials. So check this out, because we're going to do this example where I want to make a polynomial for a function that I know has no relation to 1 over 1 minus x. So we're going to do this example up here. We're going to construct the 6th order Taylor polynomial for cosine of x using that pattern that you just saw there. So if I'm going to use that pattern, I'm going to need to know the first 6 derivatives of cosine of x, and I'm going to need to evaluate all 6 of those derivatives at x equals 0. So that's what's written here. Obviously f of x is cosine of x, and I can find f of 0 by plugging in 0 for x, so cosine of 0 is 1. It's going to be the first term in my series, the constant term in my polynomial. I'm going to start computing derivatives of cosine of x. And I kind of luck out because I can take derivatives of cosine and they go in a cycle, right? So the derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is positive sine. And then the derivative of sine is positive cosine, and I'm back, and I'm just cycling through those 4 possibilities. So I kind of got a break when I had to compute the derivatives. So when I evaluate the derivatives of cosine of x at x equals 0, I get answers that go in a pattern. 1, 0, negative 1, 0, 1, 0, negative 1, 0, and the pattern is going to keep going. So now I'm going to go back to that pattern that we saw in that slide before. I'm going to form a polynomial using these terms multiplied by the appropriate power of x divided by the appropriate factorial, which is going to show up here. Okay, so you see the 1 here is the 1 here. This 0 turns into this 0. This negative 1 turns into this negative 1. And my x squared term gets divided by 2 factorial. My x cubed term is going to cancel out because my f triple prime of 0 is 0. My x to the 4th term is going to have a coefficient of positive 1. It's going to get divided by 4 factorial. So you can see the pattern that forms here. I'm going to write this a little fancier with the 0 terms canceled out. And then you can see what I get. Oops. Let me get me out of the way. Okay, so if you were asked to generate the Taylor series or a Taylor polynomial for cosine of x, it's this one that goes on forever. But I asked you to find the 6th order polynomial. So it gets this little notation, p sub 6. This is the 6th order polynomial. So it's this same long polynomial cut off after you get to the term that uses the 6th derivative. So the 6th derivative, whoops, that's not right. I even went back and fixed that. That's supposed to be a subtraction sign. That's x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So the 6th derivative is negative 1, and it's going to multiply the x to the 6th term and get divided by 6 factorial. That's how you know you use the 6th derivative. So I go up to a term that came from that, then this is the 6th order Taylor polynomial. So now let me blow your mind. That's a polynomial that only goes up to x to the 6th, so it had 7 terms in it, right? Watch what happens when I graph this. I'm going to move me out of the way. Okay, so if if I just used the first term in that polynomial, it'd be the same as the tangent line approximation to y equals cosine x. So you can see here that near x equals 0, yeah, the tangent line is pretty good. But watch what happens as you add more and more terms. If I just go to that second term, look at how well that fits. So this is a quadratic function, right? The 1 minus x squared over 2 factorial that I'm graphing. But look how closely it matches the cosine function. So you can see as we continue, that's with 3 terms, or the 4th order polynomial. Here's the 6th order polynomial that we wrote. The red is cosine of x, and the blue is our polynomial approximation. That's with going up to x to the 8th. And you can see that the more we add, the more terms we would add to that polynomial, the better and better our approximation of the actual cosine curve is going to be. Okay, your job right now is to pause the video and use that same process that we used to find a Taylor polynomial for cosine of x to find a Taylor polynomial of the 7th order for sine of x. So pause the video and do that on your paper now. This next problem that we're going to do here, we're going to find the 4th order Taylor polynomial to approximate cosine of 2x, again near x equals 0. So you could go through that same process where you found cosine of 2x evaluated at 0, and then first and second and third and fourth and fifth and sixth, oh well, here you would only need up to the 4th derivative of the cosine of 2x function, evaluate all those and use the same pattern. Or the rules that we used to transform functions in the last section still apply. So watch this. If you know the Taylor polynomial for y equals cosine of x, which I'll remind you, we just wrote it a second ago, for cosine of x, that's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So let's see. See, I even went too far. I said 4th order, so I only have to go up to the 4th derivative. And everywhere you see x, we're going to replace it with 2x. So I would say that, well, this should be approximately equal. So cosine of 2x is going to be approximately equal to, because it's not really exactly equal to, because I'm going to cut it off after the x to the 4th term. If I went to infinity, I could have left the equal sign there, and that would have been completely true. So this is going to be 1 minus, instead of x getting squared, it's going to be 2x getting squared. Instead of x getting raised to the 4th, it's going to be 2x getting raised to the 4th. 4 factorial. So here you can write out the whole pattern, but my instructions specifically were to find the 4th order Taylor polynomial, which means you're going to stop after the x to the 4th term. So down here, 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial is the 4th order Taylor polynomial for y equals cosine of 2x. And you can see, once I knew this Taylor polynomial for cosine of x, this was much easier than stopping and finding all those derivatives of the cosine 2x function. Okay, there is a list of common Maclaurin series on in your packet, and some of them you just have to know. You absolutely positively have to know the Maclaurin series for sine of x, for cosine of x, and for e to the x. The other ones we can negotiate, but you absolutely positively have to have those 3 memorized, or else. And just quickly, I kind of threw around those words, order and degree. So you could be asked to find a Taylor polynomial with a specific number of terms. Frequently they'll say, you know, write the first 4 terms, the first 4 non-zero terms of the Taylor polynomial. So then it's very clear, because you have to have 4 terms in your polynomial. The 4th order polynomial, just for example, is the polynomial with enough terms to go up to the term where you had to use the fourth derivative to figure out the coefficient. The fourth degree polynomial is the polynomial that goes up to the x to the fourth term. So just notice this. Sometimes it's clear, but sometimes it can be tricky to think about. So the third order polynomial, I'm looking right here. For cosine of x, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. The third order polynomial would require figuring out the third derivative of cosine x. But the third derivative of cosine x at x equals 0 is 0. So here, you could imagine having a plus 0 term here, and that came from figuring out the third derivative. So you would say this is the third order polynomial. It is a 2-term polynomial, and it's of degree 2 because it contains an x squared term as its biggest term. All right, so to clarify, the number of terms should be obvious. You should, if you're told to find a polynomial with 3 terms, find 3 non-zero terms. Order has to do with which derivative you used to figure out the coefficient of the furthest along term. And degree has to do with the exponent on x in the term with the greatest exponent.